And now we consider the T-shape. And again, that is the contour lines we distributed. And so from here, you can see where is the maximum strain stress would occur. Right. You're looking for the place where the maximum or larger gradient of the contour lines. Here, right?
Chamfer.
So what rules or what some of the rules you apply to determine that is where is here?
Most of the lines are together.
Yes, you got the point. The larger the gradient is, the contour lines is very close to each other. Because for each contour line represents is a constant value. For example, if you go to the morphodome, acetone, if you go to the equinox marathon, kind of combinations, okay, say some places are very deep, some places kind of flat. The deeper one is here. That is, you have to climb to the higher value in the shorter distance, and that gives you the higher gradient, equivalent to saying that is a higher stress. So the high stress is here. In particular, if this case would be like this, if really I have a corner, this corner you can see that really will exaggerate the situations, right? So here I don't want to draw that one, but you can imagine, okay? So that's the reason why for this design you do need to curve off, because the curving or round off the corner will at least reduce the stress concentration.
Quite a little bit.
Yeah, huh?
Quite a little bit.
Even by a little bit, you can improve a lot. So for this kind of corner here, that you have a stress concentration occur. We call the stress concentration is the stress they have the spike. They get a very high value in the short dimensions. That's called the stress concentration. Okay, so since right now you got a feeling about these things, so we keep moving on here. So that is a rectangular cross section, and again another viewpoint. So here is the longer side, and this is a long dimension, this is shorter dimensions. So again, this is a constant contour lines. So that means you can see contour lines will closer to each other in this direction compared to this direction, right? So that means here, around here, that is a maximum strain stress. Those information couldn't be told by the three methods just behind the screen I summarized. For there, we just do the number crunching, but we couldn't tell where the maximum, where the minimum. But from here, hopefully, you can supplement the kind of information. Okay. So, and again, for this case, if this would be the rectangle, you can see the corner here, they really barely have the largest stress. So if you corner of this one, that wouldn't matter too much. You can save certain material. Okay. And again, this is a demonstration of this concept. The same, if we round off the corner, that would help. This is the example, and here is the detailed calculations. Again, later on in the very final step, I will show you one example how to do the number, kind of one-to-one analogy. But here we can skip up this page. Triangle. For the triangle here, that is the maximum will be at the middle of each side. Okay, and this is the displacement. The question for the membrane analogy method, we do have a method to calculate your question. We do have a method to calculate, but luckily I won't impose that solution process in this class because that won't be fair to everyone here. But at least because right now we have the tools behind the screen, we can calculate, and we have a method to tell where the maximum stress, and that'll be good enough. And now to the this question: if we would have a concave shape, okay, and then that is part of your homework. If you have seen, I uploaded the homework, and so we can look at this one by one. And so if that is a cross-section shape like this, can you guess where is the maximum? If we use the X mark to mark the maximum strain stress. For this case, where it could be?
On those two sides that are congave.
Here and here.
Yeah.
Good. And how about this?
Top and the bottom.
Top and the bottom here, around here. Okay. And this one
Around the concave.
here, the middle here, right? And how about this one?
Around
And this one here? Okay, we'll look at the answers. Good. Okay, so I think everyone got
A
it.
plus, right?
Huh?
A plus for everyone?
A plus for everyone so far. Okay. So I think those kind of the skills is very important because at least before you really go to the detailed calculation, you can predict for this design where that is a series and then before this. Okay. So now go to the a little bit different topic. This method is showing that we can use the set union or subtraction of a set to help us do some calculations. The concept is this. Okay, basically this one is saying this. If we would have the hollow shaft and to do certain, this is called the parallel shaft concept, and probably you can stop and start it.